Hey everyone, I'm back. And so, as I said, don't worry about assignment number, sorry, question number 4. Don't freak out. By the time we go to the question number 4, I'm guessing that you will be ready for it. Okay. So just going into example number 2, which is example number 2 is uh, is here. Okay. So example number 2 is we're trying to design a cantilever beam. And how can you tell it's a cantilever beam? Simply, you see only a support on the left side. The beam is hanging and there is no support on the right side. So I kind of use colors, and guys, as you guys remember, my colors in my slides are not random. They are for a reason. So material properties in red here, it means I'm just trying to classify the information given to you. So the material properties, we're saying we're using a 400 grade rebar, concrete with a 30 MPa, concrete dimensions. The width of the beam is equal to 400, while the H is equal to unknown. Unknown, it means engineer choice. It means the engineer will have to decide on how much. Unlike the previous problem, the H is completely given to you. And in this example, I have no, I didn't provide such information, and I will show you what to do if the H is not given. Okay, next is resistance factors. By now, I guess you guys know that phi C always 65%, phi S is 85%, and alpha 1 is not a resistance factor. I apologize. I will have to change my slides, but it is not a resistance factor. Um, Additional information which you will need in your design, we will use 10M stirrups, 20 mil aggregate size, 40 millimeter for cover, and also the beam is exterior beam. The beam is exterior beam. Now, the loads is given to you. So the loads is given as 10 kilo Newton per meter, and that's not including the beam self weight. And for the live load is 15 kilo Newton per meter. Okay. Now you can see so far there is no moment given. The bending moment affecting this beam is not given. And you will see shortly we will be able to find what is the bending moment like before. Now, before I start, I said here H, which is beam depth, is unknown. And you can see in red here, the H is unknown. Remember, why do I need the H of the beam? Why do I need the height of the beam or the depth of the beam? For two reasons. Number one, I need the H of the beam because simply it contributes to the self weight of the beam, which is part of the dead load, and that's here. It's part of the it's the self weight of the beam, which is part of the dead load. Next is the area of steel is requires your H or your D. Remember, guys, you can build several versions of the beam with different height. Whenever we change the height of the beam, what do you think? What happens to the area of steel? It will change. If we go with a deeper beam, we need less area of steel. If I go with a shallow beam, then I need to add more area of steel. Hopefully you know why, huh? Ask yourself, why is that? I'll say it one more time. One more time. The deeper the beam, we will need less area of steel. The shallower the beam, we will need more area of steel. Think about lever arm, huh? Think about lever arm. The shallower the beam, we have less lever arm, and we have to add lots of steel. And if we have a deeper beam, the lever arm is big, and we need a less force on the rebar, so we need less area of steel. Okay, so now you know why do I need the H. But the question is how. So how do we find the H of the beam? So the code gives you some help. The code gives you some help. And this help is available on table 9.2, table 9.2. And if you take a moment to read the header, it says thicknesses below which deflections are to be computed for non-pre-stressed beams or one-way slabs not supporting or attached to partitions or other construction likely to be damaged by large deflections. So the thing is, the what deflection is very important, and you guys know if I make shallower beam, what happens to the deflection? Any idea? You're supposed to know that from your strength of material or even steel course. If I have the same span, everything the same, and we're not talking about failure, huh? So the beam is not failing, but I'm using two different beam. One is so shallow and the other one is so deep. Which one will have a smaller deflection? The shallow beam or the deep beam? Show your hands if you know the answer, please. Okay, we get Nicholas.
Deeper beam?
Deeper beam will have what, sir?
They won't like show the frick. I'm having a brain fart. I
Deflection,
forgot.
huh?
Deflection. Yeah, there we go.
Okay, thank you. I'll give you 2 marks for that. Yes, true, guys, true, because simply the moment of inertia of your beam is connected directly to the height. And guess what? It's the height cube. Height cube. So if you guys remember how the moment of inertia is related to the height of the beam, it is the width of the beam multiplied by the height cube divided by 12, I guess. BH cube over 12 for a rectangular beam, if you remember. Which means the deeper the beam, the less the deflection. The deeper the beam, the less the deflection. Okay? And that's why you can see the discussion is all around deflection. Huh? You can see thicknesses below which deflections are to be computed. Which means if I go with this H or even more, do I have to check deflection? What do you think? I know the code written, the header is not really very clear. It says thicknesses below which deflections are to be calculated. How about what I said? If I use H more than what in this table, what do you think? Should I check deflection? Looks like no, huh? Just give yourself time and you will see. Looks like no. Now let me show you the table. Not very difficult. The table comes in 4 columns, 4 columns and 2 rows. So the column you can read, please, simply supported, and then one end continuous, both end continuous cantilever. Okay, those are the 4 columns. How about the rows? It says solid one-way slab, and then on row number 2 it says beams or ribbed one-way slab. And in every row and column it gives you ln over some number, and this number varies between 8 and 10, 20 and 16, 24, 28. So kind of you divide something called ln, divide by a factor, and simply let's go to our case. So I'm asking you guys, what is my beam? Is it a cantilever, this beam here? Is it a cantilever beam or simply supported or continuous beam? Any help?
Cantilever.
Thank you, sir. Okay, so it's a cantilever beam. And which means if it's a cantilever and it's a beam, it means we go for the column and the table, and you can see here is what you're supposed to do. You're supposed to divide something called L sub n divided by 8. So your factor here is 8. Now the question is, what is L sub n? And it's here. So L sub n is something called clear span. L sub n called clear span. And I said here, see next slide for more details. See next slide for more details. So I'll skip this part. I'll come back in a minute. Huh? So what is clear span? So please look at this slide. So the clear span, you know the word span. This is not new. The word span here is not new. So if we have center lines, we measure distance from center line to center line, and we call it a span, L. Now you can see my column has a width I'm going to show you the width of my column here. So from here to there, it's the width of my column. And same from here to there, this is the width of my column. Okay, dokie. Now, and then in between, look at the name clear. So from when the beam leaves the column, so from this point here, when the beam leaves the column until it finds another support here, so we call the distance here called clear span. I'm sorry, I have an error on my slide, which I'll have to change. So I have a slide here on slide 25 and 26. Now I should label this as LN. So this is supposed to read L sub N, not L, because that's clear span. You guys got the idea? The idea is L sub N shall extend from face to face of columns, capital, bracket, or walls. L sub N may be used for bending moment, shear, deflection calculations. Okay? Because simply when you think about it, really, the beam will start to work after it leaves the support, not when it on top of your or support. So really, the bending moment should be function of Ln. And you can see in my equation here, I used Ln when I estimate the bending moment, and I said this is for simply support. So if you have a simply supported beam, and instead of multiplying times the span square, I multiply by the clear span square. Because simply when the beam is on top of the column, there is nothing the beam does. The beam only will start to work as soon as it leaves your column and simply is bridging the loads from one column to the other column. Hopefully this makes sense for you. Okay. In our problem here, the 4,000 is simply your clear span from the tip of the cantilever to the face of the column. That's called clear span. And so what happens here, look at the table, please. So I said here you must use Ln divided by 8. So which means 4,000, which is clear span, divided by 8. So you get 500 mils, 500 mil. And what does it mean? It means when I do my calculation, then I'm going to use H equals to 500. H equals to 500. And guys, this is how you find the H only if the H is not given. And here is the funny part. Now, here is the funny part. Over the years, I'm going to tell you what happens over the years. And I know that even I say it explicitly today, I know some of you will do it. So you guys think about that. We are in education and exam, and you can see not all the time your H will be a good number, like a round figure. Like let's say you divide your L by 8, you will get 487. What do you think? Do we build the beams 487? Do we? We don't. It has to be a round figure, and the rounding rule here is 50 mils, 2 inches. So what happens here? And again, that's the minimum, which means, let's say Gord, he wants to go with a 550, and let's say Martin is going with a 600. Can I say no? Can I? No, you can't. That's the code. That's the minimum, and you can use anything above the minimum. Okay. And so what happens for education setup? I cannot let you guys choose the H. I want to mark one exam. Otherwise, I have to quit everything in my life, and simply when I mark midterm exam, I have to make a 36 model answer. True, huh? That's true. Because whenever you change the H, everything will change. You will change the self weight, bending will change, area of steel will change. I have to come up with a 36. So in the exam, what I do is I simply force you to use a given height for the beam. So I can get what number and I can mark it for everyone. What I taught you is what you do if you have no such information. For example, in real life, guess what? In exam, I give you the H, and students, they ignore it, and then they go and say Ln over 8, and they find the number and do it. Please don't. If the H is given, don't use this table. Use it only if the H is not given. Are you following? Is that clear? I cannot make myself more clearer. Okay? Now.
Yes, that's clear.
Thank you, sir. Jelly, do you have a comment?
Yeah, I just wanted only to add comments on what you said about if we can use 487, because I think it's very practical that we cannot use it because of the 500 result is the result of that is the minimum height of the beam that can carry the given load. I mean the calculated load. So
No,
we
no.
cannot do under 487.
Yeah, but my point is, not all the time you get a very nice number like 500. Sometimes when you do the math here, it gives you any number. Let's say for 187. Okay. So what we have to do is we need to round it up to the nearest 50 mils, like 2 inches. Okay. Anyway, guys, please take a note and I will modify my slide and this has to read LN, called clear span, not span. Now let's see. So you can see here, I'm in a way better situation because look at this. I started with I don't know the H, but now I know the H. The H is 500. Now, no, since I know the H is 500 and I know the width is 400, I can find what? I can find the self weight of my beam. If you guys remember, sometime in my course, I give you the rule. Very simple. You take the width of the beam, multiply by the depth of the beam times how much? Times gamma concrete, 24. If you do this, what you get is you get 4.8 kilo Newton per meter. This is the self weight of the beam for every linear meter of the beam. Please write it down. Do not multiply by the length of the beam. Do not multiply the self weight per unit meter by the length of the beam. We don't need that, huh? We need the weight of the beam per unit length, please. Then guys, remember, if you guys go back here, I said your beam already carrying some other weight from the slab. You can see the number is here. So it's supposed to carry 10 kilonewton per meter, and that's not including self weight. And that's where I found the self weight. Then I'm going to add it to the 10. Because the 10 comes from other element like slab. You can see here, I added the 10 from the slab plus the self weight. So finally, your beam, it's supposed to carry a 14.8 kilo Newton per meter as dead load. Now we want to find my moment. Guys, look at this, please. Your factored moment is function of W factored. How can I find my W factor? Remember, when we talked about loads, we said, you know what? Yes, we do have dead load. Yes, we have live load. But the reality is, live load doesn't affect the beam by itself. When they act together, and that's where we came up with something called load combination. Okay? So you can see what you have to do is you have to simply try to find what is the worst case. So I should try load combination number 1 or load case number 1 and then load combination number 2. And if you guys remember, load combination number 1, you have to multiply dead load by 1.4. So I took this number 14.8 times 1.4, I got 20.72. Now there is another load combination which is 1.25 dead load, which is here, plus 1.5 live load. Where Tahir got those? It's from the building code. Building code completely defines the load combination as we did back then. Okay. So all you have to do is you replace, you apply here equation very simple. So 1.25 times 14.8, which is total dead load, plus 1.5 multiplied by 15, so you get 41. Now let me ask you, so there is one load case, your beam will be subjected to 20.72, another load case where the beam will be subjected to 41 kilonewton per meter. Which one you think I should use in my design? What do you think?
Get the maximum.
The maximum, exactly. Thank you. Why is that? Because oh my God, if I design for 20.7 and the other low case happen, it means you know what happens, huh? I go to the jail. You have to simply, you have to literally go to the jail because somebody will die, huh? So simply, as a designer or engineer, you have to think about what is the worst case scenario. Again, it's very simple, very intuitive, huh? We will use design for 41 kilonewton. And you can see, here we go. So I take this 40, which is the maximum of all possible load cases. In my example here, it's only very simple, 1 and 2. But guess what? In reality, you could see so many of them, if you remember, huh? Because we have a snow, we have wind, we have to try all the possible load combination. We talked about this one. But again, in our class here, I will always give you, same as you see, dead plus live. So you have to try 1.4 dead, and also you have to check 1.25 dead plus 1.5 live, and then take the maximum. In real life, we have to try all of them if all of them are possible loads. If you're designing a floor, how can I get snow? If I'm designing a floor beam, there is no way for a floor beam to get snow. But if it's a roof beam, then yes, the roof beam might get snow. So yes, we have to try all, but all possible load combination. Now, so what happened here? Once your W is ready, the WF, which is factored load, you simply use it to find the bending moment. Now, here is something that we will fight on it. We will fight. You will see that. Okay. So what I did here, I said, okay, so the MF, which is the factored moment, equals WF multiplied by L square over 2. Okay. And I wrote my numbers so you can see my span is 4. So 4 times 4, that's 16. So W squared, L squared, multiplied by WF 41 divided by 2. So I got this number. Some of you may think, why Tahir never used WL squared over 8? Why I haven't used WL squared over 8? Guys, here is what pisses me off. The equation is simply depending on the structural system. You guys know that structural system, it means it can be cantilever, it can be a simple beam, it can be a continuous beam. There is not a single rule that applies or single math equation that applies for all of them. Cantilevers, we use WL square over 2. A simply supported beam, we use WL square over 8. Continuous beam, this is at the very end of next class. Okay? So guys, please be mindful. Check the system before you write the equation. Every year, what happens is, I give you example cantilever, and then let's say midterm is simple beam. People, they don't care. WL square over 2. It is for a cantilever. If the system changes, it went from cantilever to a simple beam, then please change the formula as well. In my slide here, I have everything. All you have to do is read the slide. Now, next is we simply found this beam. Now, you can see now I'm at the same moment. Same stage as last problem. In the last problem, you guys haven't done this, huh? Remember, this business is new. For example, number 2. In the last problem, the 800 was given to you. The moment, as Gord said, probably not. And thus you can see there are some calculation that has to proceed to the area of steel. So you can see I have my moment. Here is my moment. And now it is time to find the area of steel. Guys, remember, the area of steel, we use D, not H. I'm very clear, huh? In the area of steel, we use D, not H. D is the effective depth of your beam, while H is the overall thickness of your beam. And guys, we agree that in my class, we will always make this assumption as a trial. We will try. So we go from 500, we take 70, and then we left with 430. What this 430 is the effective depth of the beam, which goes into your equation. You can see it's here, 430, and then 430 here. You guys, this equation, we derive it together in our class, and we've used it last class. And then here we go, we got 2660, which means I need to provide in my beam minimum of this number to make my beam able to resist this bending moment here, 328. Now, if you guys remember, we had the discussion, which is what are my options? You can see, as we discussed last class, we can choose a smaller bar diameter, so we end up with more bars, or we can use a larger bar diameter, and we can end up small bar. If you guys cannot remember, this was in my slides. I'll take you quickly that this discussion, huh? You guys remember the discussion that we said there are so many options? Okay, so again, typically in my exam or my assignment, I make your life easy and I don't leave you in this problem. I just give you, you know what, use 20M or use 25M or use 30M. And once this is ready, what happens is, all you have to do is very simple. You divide the 2660 by, so if I tell you use 30M, what happens? If I tell you use 30M, guess what? We know from the chart that every 30M has a 700 mil square of steel. So all you have to do, you divide this by 700, you get 3 point something, and that's where I said, you know what? Use 4. And if you use 4, what happens is, you just you say area of steel actual, because that's really the actual steel that will go into your beam, equal to 4 multiplied by 700, then you get 2800, and you can see it is more than 26. Okay, guys, you guys remember there was an assumption made. Where was the assumption? The assumption is here. We need to make sure that this assumption is happening before we finalize our design. How we do it? We do it this way. We go ahead and say, let's find what is B minimum. And the B minimum is the minimum width of the beam. Accommodate all those bars in one layer. Because one layer and two layers, this will make a huge difference in this 70, huh? So again, we found out is if it's one layer, let's do it, huh? So how we do it? We say, okay, you know what? We have to provide cover from each side. And then we have to provide stirrup 10M from each side. And then finally, we have 4 bars of 30M. And then in between, we have 3 spacing, and each spacing minimum is 42. If you don't, guys, if you don't remember this equation, go back to last class. And if you don't remember how do we find the 42, which is the minimum spacing between the rebar, please read the slides. Okay, so you need to make yourself like a note. Where did I get the 42? The minimum spacing between the rebar. Anyway, so you can see here, based on this math, the minimum width of the beam that can accommodate the 4 bars with the proper cover and spacing and stirrup is 346. Now, my beam that I'm trying to build is 400. It means my beam is wider than the minimum. It means, yes, it can accommodate all those bars in one layer. And since we know it will fit in one layer, it means now I know my rebar layout or geometry. Now let's go ahead and find my G actual. So very simple. We go start from H and we subtract the actuals. Cover here, cover is 40, and then stirrup, and then 1/2 bar. Guys, always you have to visualize and imagine what's happening at the bottom of your beam. Always. You have to imagine, visualize what happens at the bottom of your beam. Like the anatomy, huh? So we have here 435. And guess what? I started with 430. What went into the equation is 430. Am I okay? Am I good? What do you think?
You are good.
We are good. Why? And it's written on my slide because simply we ended up with an actual D, which means implicitly lever arm more than what we originally assumed for the lever arm. Okay? So that means what? That it means my area of steel is okay and I don't have to repeat my calcs. Repeating the calc is a refinement in this case. It's not a must, it's a refinement because maybe or maybe not change your area of steel and maybe yielding to some saving in rebar. However, if it's the opposite happening, there is no other choice. You must calculate area of steel, and that's in the slides. Please read. Now we know we're going to provide 4 bars of 30M. Let's go ahead and check minimum and maximum. Minimum is we go ahead and divide area of steel divided by the width of the beam divided by the actual depth of the beam. So we get 1.61%. Less than 2.7. Where did they get 2.7? Is that secret? It's here. It's very simple. You go ahead, divide by the FC dash by the 1100, 2.7. So what turns your beam into balanced failure is 2.7% reinforcement. How about the case now? We only have 1.61, which happens to be less than 2.7. It means tension failure. It means great. That's one check. The other check is what should be minimum area of steel. So very simple. The only tricky part is the H in the equation. The equation is function of H not D. You can see I used 500. Anyway, you can see here 547 millimeter square of rebar, and that's the minimum. Are we okay? Yes, we're okay, because simply we're adding 2800, and then the minimum is 547. It means we are above the minimum. So finally, we are above the minimum, below the maximum. It means life is good. It means my design is fantastic. Done. And that marks the the ultimate limit state, ULS. So this line here, this little calx marks the end of ULS. Are we done? Not yet, because we have to do SLS. What is SLS? We do only one thing, which is cracking. Okay. Now, before I go to the cracking, you guys remember that when we do the SLS cracking, how many zones do we have? Martin, can you show me with your hands how many zones? Thank you, sir. Gord, how many zones? 2, huh? 2. Zone number 1, zone number 2. Okay? So zone number 1, it's all the time. No matter what, we always check zone number 1. Zone number 2, we have to check the beam depth. Only if the beam exceeds 750, then we do it. And you can see, you guys remember what was the depth? It was 500, which means you can see, look at this box here. Since my beam is 500, it means less than 750. It means no need for skin reinforcement. How about the last check, which is below, it's zone number 1? Very simple. Remember, it's one layer. I know I haven't put here the sketch, but I'm hoping that you guys can visualize. So DCS is distance from extreme fibers in tension to the nearest rebar layer. I'm lucky here because I have only one layer of rebar. One layer, huh? Okay, because I have one layer, it means cover plus stirrup plus half bar. Give me a second, please. So I have one layer of rebar, you get 65, and then good news is for area, which is the area around flexure bars per bar. So you can see here, that's the width of your beam. This is the width of your beam. And this is your D sub D, your Y, which is the same as DC. And then you mirror, so you multiply by 2. And then don't forget, we divide by the number of bars, which is 4. Very simple. What I got is, for the crack control factor, is 22,690. And remember, the beam is exterior. It means it has to be less than 25,000 for your beam to pass the control check, the crack control check. Are you guys following so far? I need some noise. Let's check on.
Yes.
Let's check on. Let's check on Siham.
Yes.
Okay, let's check on Mr. Diego.
All good.
Raymond.
Hello, yeah, following.
Excellent. Okay, guys, I think things will go faster because now we have 20 minutes and I can show you, probably we can also go through some other stuff, huh? So here we go. This is example number 3. And could you please identify what is the structural system for number 3? Show your hands, please. Identify the structural system for problem number 3. Okay. We have a customer who is very, very active today. Let's go with Nicholas.
Simple beam.
Thank you, sir. I think that's enough. We'll give you 2 marks for that. So yeah, the beam is simple beam because you can see the column, it has column, actually 2 columns. And so we call this one simply supported beam. Okay. Again, I'm not going to waste any time. You guys can read. We're going along the same line kind of copy and paste of the previous problem. H is not provided. So H is the engineering choice. We don't know so far. And we have some loads. So the loads are 30 for dead load, not including self weight, and then 15 for live load, without including, I'm sorry, that's it. So again, this will go very fast. Look at this. So we're using exactly the same table before that simplifies for us what should be the minimum thickness of our beam. You can see here, I didn't waste your time, but I give you the clear span right away. But just in case, if you are given the span and you want to find the clear span, obviously you have to find what is the thickness of your column. Are you guys following? If you're giving center line to center line span, you want to find clear span, then you have to know what is the column dimension. Now, because it's simply supported and it's a beam, then looks like I have to divide my span by 16. 16, okay? That's from the table. You can see here, I simply divide my span, clear span by 16. I got 562. I rounded to the nearest 50, and remember up, because that's the minimum. So you cannot round it down. So you round up to the nearest 50 millimeter. So we start our design with 600 millimeter. And now I know that my beam width is 450, my beam height is 600, so I can find the self weight of the beam. B times H times gamma concrete, always 24 in our class. And then we got 6.5 kilo Newton per meter. And I will say it one more and last time. Please do not multiply this number by the span of the beam. We want to find the self weight of the beam per unit length. Then what you do next is you simply add the self weight to whatever comes to this beam from a slab. Then we end up on this beam of 36.5 kilo Newton per meter. We do the same business. We simply have to go through the load case number 1, load case number 2, or load combo 1 and load combo number 2. And once we got the maximum, which is here, 68.1, then we use it in the formula. What formula? Look at this, please. Do you see this 8? Why 8, not 2, like previous example? Because it's simply supported beam. Okay? Simply supported beam. So you can see now I have my moment is the moment on this beam will be 689.5. And then once you do that, you follow through. So you go ahead from your H, you take 70 as assumption, and you got 530. Use your design equation based on 530, not based on 600, and then you get area of steel of 5367. 5367, 5,367. Okay, now, guys, what's coming is fun. Are you ready? What's coming is fun, because you know what? I'm gonna prepare you emotionally, then I'll do it. So in the previous example, everything was linear, straightforward. So you go from one step to another step to another step. We never had to go back. We never. Everything was linear. You will see this is not the norm. Or I'm not saying it's the norm, but I'm saying is you need to be prepared that you at some point your numbers doesn't work, then you will have to go back and do something else. Okay? And you will see this shortly. Are you guys ready? Example number 1 and 2, straightforward. We never had to change anything. Every check we say, okay, 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 okay. What happens if it's not okay? Let's see what happens. Please get ready. Please focus. If you have been sleeping for the last 1 hour, 30 minutes, it is time for you to wake up now. Okay, let's see. So now we can see I'm saying, you know what? We need this much. So I said try to use A30M, because it's very simple. You divide whatever the number you get from the equation, you divide by 700, you'll get 7 point something, and we cannot add 7.5, we have to make it round number. So we end up saying, okay, 830M. And 830M is your actual steel for now. And remember, for now, it means for now, at the moment, but maybe change in the later on. But for now, I'm going to say area of steel equal to 8 times 700. Area of steel is equal to 5600, which more than this number, then we're okay. Now let's go ahead and see, can I fit all those 30M in my beam width? And that's the norm, by the way. There is nothing new. Once you came up to close to the end, you must verify the assumption. And how you do it, you must know, can I lay my rebar in 1 layer or 2 layers? That's how we do it. Okay, very simple. 2 cover plus 2 stirrup plus 8 bars plus 7 spacing. Always, guys, remember how Tahir got this 42. Again, go to the slides. Okay, so we need 614. What does it mean? What does it mean? It means, and remember, my beam, if you go back, my beam is only 450. 450. So the answer is very clear. No, you cannot place the 8 bars side by side on a 450 millimeter beam. So it means I need 2 layers. I need 2 layers because simply your beam width is less than B minimum. Remember, B minimum based on the assumption of one layer. So what I did here is I repeat the same process, but trying to find another B minimum, but based on how many? Can you read that? 4. Because we have 4 bars and we have 3 spacing. So if you want to lay 4 bars in your beam with the proper cover and spacing, you need 326. Guys, what does it mean? It means those 830M can be placed in 2 layers. Are you following? So they cannot fit in 1 layer for sure, but they can fit in 2 layers. Each layer will have 30M. Okay, now let's see the comments. Okay, let's see. So what happened here is you're gonna go ahead and simply find what is your actual G if you have 2 layers. Okay, so if you have 2 layers, guys, we've done this early in the class. If you have 2 layers, please don't waste your time to find where is the centroid. The centroid is in the middle of the spacing. Okay, so you can see here 600, that's my H, and then cover, and then stirrup, and then 1 layer of rebar, 30M, and then finally spacing over 2. So which means your actual G is 509, which is less than what we originally assumed. So the question is, and actually the question I don't have to ask because it's in my slide in red, bolded, underline. I don't know how can I be more clear. So it means in this case we must repeat AS calculation. So what we do is, you can see I took the 509, put it in the same equation, okay, and got the new area of steel. So we have how much? We have 6,000 and then 23 square millimeter of rebar. Now, okay, oh my God, that's a problem. You guys see the problem? Does anybody in this class see the problem right now? So I got the new area of steel. I'm sorry, the new D or the actual D. When I place it into the equation one more time, I got 6,000. Do you see any problem?
Yes.
The amount of steel that's needed.
Yes, sir. Look at this, sir. Please look at this. Compare this number against my A30M, which means my A30M is not sufficient. Is not sufficient. Okay. So look at this. What Tahir did. So I said, you know what? Try in red, and by all means, it's try, because it's not so far nothing is confirmed. It's try. So I said, you know what? Use 1225M. And so what I did, and is I simply try to see what is the minimum width for 6, because I know 12 is too many. I don't want to waste your time or my time to try to fit them in 1 layer. Too many. Okay. So what I did is I said, okay, let's see if I can accommodate half of the 12 into one layer. So I went in 2 times 30, 2 times 10, 6 times 25, and then 5 times 35. Guys, please, again, make sure you understand where did I get this 35 mils, huh? Go back to the slides. So I need 405, okay? And so the minimum, so my width is 450. It means it's more than 405. And guess what? Yes, I can use 2 layers of 625M. Okay, and what happened here is, do you think my G actual will still be the same? Do you think my G actual, so I got my G actual before as 509.
It should stay the same because it's still symmetrical and in the center, right?
No, sir, I'll tell you why. I'm sorry, that's kind of, I know it's kind of deceiving and tricky. Look at this. Please look at this. So when you estimate your G actual, it is function of the spacing, and the spacing is function of the bar diameter. So if I change my bar diameter, the spacing will change. And remember, it went from 42 to 35, from 40 to 35. So I saved 7 mils, huh? And the other thing is your bar diameter, which is included in your G prime, also changes. And this is what happens when you try to find your G one more time. Look at this. So this is the same, doesn't change. This is the same, doesn't change. This one is the same, doesn't change. However, this one changes. Guys, please refer to this one as well, huh? And this one changes. I put them in a probably different color, huh? So let's color them. Let's color them. So let's put this one as, let's say, green, and this one green as well. Between this and this, so those numbers have changed, huh? The bar diameter and the spacing as well, they change. Please take a look, huh? Take a look at those numbers. Now you can see I got a different G prime, G actual. And what happens here, if I go back to the same equation one more time with a new G actual, okay? Here we go. So here's my G actual. Guess what? I got 5721. Does it make sense? It makes sense because simply I gained more lever arm. When I gain more lever arm, I simply get less area of steel. Okay, so now I needed 5721. And remember, is that good or bad? It is good because 5721 is less than 6,000, and 6,000 is your 1225M. It's here, huh? Look at this, please. So this 6,000 is here. It's your 1225M. We're done because now everything matches everything. Now I have a 1225M on 2 layers, and simply whatever the D in this case, it requires area of steel more than the 1225M. Is that roller coaster, huh? Roller coaster problem. It's iterative, huh? And you can see, please, this is the design. Whether you like it or you don't like it, this is the design. The design is never a linear process. The design, sometimes, if things doesn't work or don't work, then you'll have to go back and refine your numbers. Gord.
That one does a good job of showing the importance of those checks, though.
Yes, true. And just wait until next class, and you will see on next class the real roller coaster problem. It's just like that. You will see. Anyway, just be patient, huh? Now, next is once we're done, this probably marks the end of ULS, ultimate limit state. And so what you have to do is, oh my God, wait. I think I'm not following 100%, but I don't know why I label this as crack control. It has more than, anyway, so please don't mind the title. So get rid of this title and things should be okay. So check failure mode. And remember, we're not done yet. We have to make sure it's not compression failure. We haven't done this yet. So you have to estimate your row balanced, which is 2.27% based on the 25 concrete. And then your actual row is, you just have to divide area of steel. Remember, we have so many area of steel. We had, look at this, how many of them? 1, and then 2, 3, 4, probably you have 5, 6 numbers. What you're gonna use is your final decision. We're going to add 1225M in this beam, which means 6,000, which is 12 times 500. And what we get is, we got 2.57%. Oh my God, more than 2.27%. It means compression failure, compression failure, okay? And what happens here, to keep on the roller coaster, what I did is I said, okay, you know what? It doesn't work, compression failure. Can we fix it? Or sorry, if it's compression failure, should I just ignore compression failure and I say my beam is safe? Because remember, look at this. And I said this several times. There is no relationship between beam is safe and compression and tension and balanced. Those are two different topics. You can see my beam is safe. My beam is safe, but if it's to fail, then it will fail in compression mode. And what I did is I propose, which will be super easy. You can change the depth of the beam. You can change the width of the beam. You can change FC dash or add compression rebar. So what I did here, I said, okay, let's see if F prime C 30 will do it. So I repeat the whole problem one more time based on the 30. Everything stays the same. Look at this. So your D prime, I'm sorry, the D actual is the same. You can see same D prime, which means I'm still using my 1225M. No change. The only change is, I simply use 30 MBA, which is here. So here is your 30, and here is your 30 one more time. So I got 5,077 millimeter square of rebar, and then I did my check very quickly one more time. Row balance increases. So here is your row balance. It went from 2.27% to 2.7%, and then my row for my beam still the same, 2.57%. However, this is less than row balanced on this side. It means tension failure. And you guys can see, in a matter of one step, I'm able to fix my beam by changing my beam from 25 MBA to 30 MBA. And then finally, we check S minimum for sure. I just did it for you guys, but I know because I'm very, very close to the row balanced. So obviously, I'm very, very far from minimum. If you guys don't remember, if I go back to my lovely slide here, which I started today, okay, this slide here, this slide, I'm very close to here, to this side, very close to row balanced for sure. I'm away from my minimum, but I did it for you guys, okay? So it means we're okay. It means finally I'm able to make my beam work. And let's see, next is assembly or crack control. I will leave these guys for you. Please do it on your own before you come to the next class. No measure, nothing measure. The difference is this is not really this is not a one layer, this 2 layer, and that's where you see DC. You can see DC is 52. However, this number is not 52 because one goes to the last layer of rebar and the other one goes to the centroid. Again, please do it on your own. And with this, I finish question number 2. I'm sorry, question number 3. Okay, guys, remember that we don't need any skin reinforcement because my beam height is 600, while it has to be more than 750 to start asking for skin reinforcement. Okay, guys, any questions so far?
Sir.
Go ahead. Actually, we are 2 minutes over time, so if you want to leave, that's your choice. I cannot force you to stay. If you want to hear the question, hear the answer, you might stay, and it will be in the recording, whatever. So if you are in rush, please leave. The answer will be in the recording.
Sir.
Go ahead.
Your first approach is changing the F prime C. And if that is still not working, we can always apply all the changes, right? We can go try the width of the beam, try to change the width of the beam, right? Until we got into make it.
To be honest, I'm telling you, the beam width and the beam height, those are controlled by the architect, and architects are not really easy because probably they have done their exercise. And why they give you 600? Because it conflicts with other elements in your building. Okay.
Yeah, I know. But what happened if your if prime is still not working? So you have no choice.
No, compression rebar is your last resort, and it will work no matter what.
Okay.
Compression, guys, compression rebar is your last resource, and it will work no matter what. If your architect say no for the weight of the beam, no for the height, or your F prime C becomes like crazy, like 35 or 400, sorry, 40, that's too much, huh? So then your last resource is adding compression rebar. That's your last resource. Guys, any other questions? Okay, guys, Martin, your question is about your midterm exam. It will be in the email that I'm going to follow tonight, but it is up to assignment number 3. So basically, I will examine you on statics review and snow, live dead snow and bonding, and then finally on beam checking. Okay, beam checking. But you will see this on the email tonight. It's going to be a long email because I have to put all the information. And again, if you still have any question after the email, please email me back to cover it for everyone. Formula sheet, guys, the exam is an open exam. We are online. I don't know how can I control it's not open book. You are on one side. I have no way to control that. And by the way, ever since your exam concrete was open book, it is up to the students to prepare their formula sheet. And by the way, I have to say that in the recording and for everybody to listen to it. Formula sheet is not optional. Please don't come to my exam without formula sheet, because simply it will take you forever to solve the exam. Formula sheet is just kind of a saving you for you to flip through all the presentation or all the print out of your exam. So please ensure you have your own formula sheet. How, when, where, it's not my responsibility. I give you a slide, you go through it, you solve it your assignment, and simply in the assignment you use some formulas, then put them in a way that fits your needs. I'm not going to do that. It is your call. Any other questions regarding the midterm exam? Okay, guys, if you have no questions, I will let you go and have a fantastic day. Thank you so much.